This is going to be a brief review of some of linear algebra. We're going to start here with some matrix definitions and operations. So just to remind you, a matrix is a rectangular array of typically numbers that are ordered in rows and columns. This notation here says that there are m rows and n columns, and the entries are real numbers. If we wanted to have complex numbers, that r could be replaced by this complex c. And so we typically use capital letters to denote the matrix, and the entries inside are usually the lowercase version of that letter. And the lowercase notation here for the index says that this is the ith row and jth column and denotes that entry. Sometimes when it's convenient, we'll use this square bracket notation to identify the element, the ijth element. If the number of rows and columns are the same, then we call it a square matrix. Otherwise, we say that it's rectangular, and we can have wide rectangular matrices and we can have tall rectangular matrices. We can think about vectors as a specific type of matrix. In particular, we can talk about a row vector that is simply just one row. It's a matrix that has only one row and a certain number of columns. And likewise, if there's only one column, we can talk about the matrix being a column vector. And oftentimes, if we wanted to denote that vector and think about it more as a vector than a matrix, then oftentimes we'll use the lowercase letter to denote a vector. Just a couple basic operations. You recall that we can add matrices, add or subtract, and so the dimensions of those matrices must match both the rows and columns. And so we can see that here's how we write it in matrix notation, and then we can also use index notation where we're saying that this is true for all choices of I and j, where I and j belong to their respective ranges of numbers of rows and numbers of columns. We can also multiply matrices. In multiplying matrices, the important part is that the interior dimensions match, and the exterior dimensions, m and p here, give the dimensions of the resulting matrix. So C is a matrix of m rows and p columns. When we multiply matrices, there's a special way in which we do that, and I'll show you an example in 2 slides. But in index notation, we can say that the ijth element of the resulting matrix C is equal to a sum over k, and k is the interior dimension, and this is a vector that is the ith row of A, and this is a vector that is the jth column of B. And so you'll see that symmetry when we do the multiplication example. A couple more properties. Addition and multiplication are associative, which means that we can choose to add A and B and then add that to C, or we can choose to add B and C and then add that to A. Similarly, we can multiply AB and then to C, or we can multiply BC and then to A. The trick there is that even though both of them are associative, multiplication is not commutative. And what this means is even though you can choose, essentially you can multiply these BC together before you multiply it by A, you can't switch the order. And so in multiplication, in general, the multiplication order is important, whereas addition is not. A few more definitions. The diagonal of a matrix are all the elements where the row and column index are the same. So this is simply just A11, A22, A33, and so on. Typically, we do this for square matrices, but it is possible to use this definition for rectangular matrices, and just make sure you keep in mind that the row and column index are the same. The transpose is an operation that flips the matrix over the diagonal, and so this is one case where you might define diagonal even for a rectangular matrix. If the original A matrix is m by n, then the resulting matrix is n by m, and so you can just think about that as the ijth element of the transpose is the jith element of the original matrix, and so we're just switching the role of row and column. We can talk about a square matrix being symmetric if the matrix is equal to its transpose, that means after you flip it, it's the same matrix. And so no matter if it's symmetric or not, if you flip a matrix twice, you take the transpose twice, then you get the same matrix back. Another operation we can have on a matrix, again, typically a square, but you could generalize this, is just the trace, and it's the sum of the entries on the diagonal. So all those entries that have the same index of row and column, we just add those up, and that is the trace. An interesting property here is that even though the multiplication operation is not commutative, AB is not equal to BA, the trace is in fact equal. And so it's a nice property that we can sometimes use to prove some things. Okay, so here are my examples. If we have a matrix A is a 2 by 3 matrix, B is a 3 by 2 matrix, and B transpose is a 3 by 2. And so you notice that this is the diagonal of this rectangular matrix. Those are the elements that have row and column index the same. And so those stay put, and everything else flips across this diagonal. So you can think about this flipping across the diagonal, and that's what results in B transpose. When we multiply A and B, we're essentially taking dot products of the rows of A and the columns of B. And so in order to get this first element of the product, AB, this is composed of taking the dot product between this row of A, the first row of A, and the first column of B. And so this is A11 times B11 plus A21 times B21 plus A13 times B31. And so that's what's given by this element here. When we move to the next element in the first row, that means we're still going to use the first row of A, but we're going to use the second column of B. And so by taking the dot product between the first row of A and the second column of B, we get this entry. Then when we move to the next entry, to get this, we're going to use the second row of A and the first column of B. And that produces that entry, and you keep going. If we took the trace of the product AB, then this element here is simply just this first element. It's the first element of the diagonal. This second element is the second element of the diagonal. And so this may be one example of a time when we might use this square bracket notation, where we'd say AB11 plus AB22.